This is David Van Vranken here at UC Irvine, here in Chemistry 51C, and this is our fourth lecture in the Chemistry 51C series here in fall of 2020. It's the academic year of coronavirus, and I just super appreciate the fact that you guys are coming into the lectures and listening live or at home. Any way you want to get the content, that's awesome. I want to encourage you to keep practicing working problems in organic chemistry, in the textbook, in our online homework system. That's really the way to learn problem solving in organic chemistry. I wanted to start our lecture today talking about something that I see over and over again in the news. Usually I keep track of what's happening in recent events. I usually type the word molecule into one of these aggregate news sites like Google or Bing or something to see what comes up. And I keep seeing news stories about this guy, Alexei Navalny, who is kind of an outspoken critic of the leadership in Russia. And recently he was subjected to poisoning. And here was a news article I traced back to that talks about how German military scientists likely identified the nerve agent that was used in his poisoning. And so it got me interested in this nerve agent, which the word novichok keeps coming up. I don't speak Russian, but my understanding is that novichok means basically newbie in Russian. And novichok is not a molecule. There's no chemical structure for novichok. It's actually a class of molecules, a new class of nerve agents. They're way more dangerous than the traditional nerve agents that were developed, I don't know, in the 1970s or 1980s, known as the VX reagents. Just super scary, off-scale scary. So novichok is a member of a class of chemical warfare agents that target the nervous system that are referred to as binary agents, meaning that you can have two different chemicals that are not, either one is not super dangerous by themselves, but when you put them both together in some sort of an artillery shell or a bomb or something on the way to the target, they can mix together or somehow before you aim them towards the target, they mix together and undergo a chemical reaction to form the final nerve agent. So the nerve agent the novichok agent that I saw referred to in that Science article was referred to more specifically as A234. And A234 is a fluorophosphonate, like sarin gas is a well-known nerve agent used for chemical warfare, has a fluorine attached to a phosphorus. And you generate these from two different reagents. That's why it's called binary. They mix together and spontaneously form A234. And normally as a synthetic chemist, it would bother me to have a byproduct in there that I couldn't purify out. But in this case, the side product, the byproduct of the reaction is HCN, hydrocyanic acid. That's what they use in gas chambers to kill people. It's super toxic. So I guess there's if you're trying to hurt people, I guess there's no problem having that as a byproduct in this process. And so how would you determine if somebody was exposed to A234? That sounds extremely difficult because this is chemically reactive. Nucleophiles of all types, including water, sulfur compounds, things that you have inside of cells and in the human body, are going to tend to add to that phosphorus atom and substitute the fluorine. And in particular, there's a class of enzymes that you have in between nerve cells at the synaptic junctions called acetylcholinesterases, which get rid of the acetylcholine so you can have the next nerve signal. And these fluorophosphonate derivatives like A234 form a covalent bond to the acetylcholinesterases. And so the neurotransmitters stay in between the nerve cells and keep signaling and never stop. And that ruins neuronal signaling that controls, I think, things like lung function, brain function. So how would you tell if somebody was exposed to this? If, as a chemist, to me, the most unambiguous method would be to get some of this A234 that hadn't reacted from the clothing or from a bottle, and then detect that using mass spectrometry, which is extraordinarily sensitive. Things like NMR or IR are not at all sensitive. You couldn't really use those. You'd have to use mass spectrometry and just say, based on the molecular formula, oh, I found some left over on the clothing. But they were suggesting in this Science article that what they might have done is they might have been able to extract out, maybe by taking a blood sample, extract out enough of the unreacted A234 from the lipids inside of the red blood cells or other tissue that they might have isolated in order to identify that molecule using mass spectrometry. The alternative is they could have tried to isolate some of the enzyme targets, and then and if you isolate enough of the protein, you can cleave the protein into little pieces and identify whether A234, the mass of A234, is now attached to some of those protein fragments. That's a lot harder because it's hard to get enough protein out of tissue samples that you get from a person who is still alive in order to determine that. So novichok, those novichok agents sound really scary. I mean, they don't sound as effective as just shooting somebody, but I guess if the point is to try to make people afraid of chemicals, maybe this is one way to do that. Okay, that's an awful use of organic chemistry, but it's better to understand what's going on. Let's go ahead and return to our lecture. And what kind of stuff have we been talking about here in our organic chemistry lectures? So we left off talking about regiochemistry in electrophilic aromatic substitution. And I gave you this really super important list that you need to memorize that lists functional groups on benzene rings and whether they activate the benzene ring and make electrophilic aromatic substitution faster, or down at the bottom of the list, whether they deactivate benzene rings and make electrophilic aromatic substitution slower. And moreover, we were able to divide those substituents, those benzene ring substituents, into classes where we could predict ahead of time whether the next substituent will be added ortho or para to the first substituent, or whether the next substituent will be added to a meta position on the benzene ring. And so this is what we're going to come back to today. I told you on the last lecture that what we're going to focus on today is what happens if there's two substituents on the benzene ring. How do you decide whether the third substituent you add is going to go ortho or para or meta versus which of the two substituents? And I'm going to give you a simple rule that allows you to decide when there's two substituents on there, how do we decide where the third substituent is going to go? And the rule that we're going to use, this critical rule, is that the strongest activating group, if you have two groups on a benzene ring, you look for the strongest activating group. It's the one that's going to control the regiochemistry. And not everything is an activator, so you just look at the group that is highest in our vertical list here. So the least deactivating group would be the strongest activating group. So you just look at the group that's highest in the list, and that's the group that's going to control the regiochemistry. Let's take a look at this example here where we have, I think this is called cresol, this phenolic compound, where there's an alkyl group here at the bottom and a hydroxyl group here at the top. So when we look at these groups, the alkoxy group, the OH or OR compound, so R here in our list can be R or H, that's higher than an alkyl group, right? An alkyl group is down here. So this is the group that's going to control the regiochemistry. So let me go ahead and just make a point of that. This OH group controls the regiochemistry because it's highest in the list. Controls regio. And alkoxy groups or ortho-para directors. Remember, everything above this line here is ortho-para. And everything below the line is a meta-director. So the hydroxy group controls the regiochemistry. That means when we brominate this ring, and I told you that we don't really need to have ferric bromide when we brominate phenols that have OHs on them. So when we add the third substituent here, when we brominate this ring using Br2, we don't need to add FeBr3 with hydroxyl compounds. It's going to go ortho or para, but the para position is blocked. We can't substitute, we can substitute H, but we can't substitute alkyl. So really the only choice is to go to one of these two ortho positions because the para position is blocked, and that's the answer here. So you need to know two things. You need to have memorized this list of activators and deactivators and in the correct order in order to decide whether hydroxy or methyl is higher in that list. And then you need to know whether that group is an ortho or para or a meta director, ortho para versus meta director. Let's take a look at another example down below here. Let's suppose we have a carboxylic acid para to an alkyl group, right? It could be methyl, ethyl, T-butyl. So if we look at what's highest in the list, now we're trying to compare some sort of a carbonyl group, which could be a ketone, an ester, a carboxylic acid, an amide, with an alkyl group. This time, the alkyl group is higher in that list. So let's go ahead and note the fact that it's the alkyl group that controls the regiochemistry in this case. So I'll just write that here. It's the alkyl group that controls the regio. So alkyl group controls the regiochemistry, and the alkyl group is an ortho para director. So the next substituent, which is going to be a sulfonic acid, is going to go, it depends on whether the methyl is ortho para or meta directing, and that's an ortho para director. So remember, that's ortho para directing. So the next substituent, the sulfonic acid, is going to go either ortho or para to the methyl group, and the para position is blocked. The position that is para to that methyl group is blocked, so the next substituent is going to go ortho. So one of these two ortho positions, doesn't matter which, is going to get the sulfonic acid group on there. And there we go. That's how you use this simple, powerful rule that you have to practice. I promise you, if you wait until the exam to start practicing this rule and guessing products, you're not going to be able to figure it out. You've really got to practice using this to be able to make powerful predictions. And I'm sure I'm going to ask you this. I'm positive. Everybody who teaches organic chemistry the third quarter will ask you questions of this type. So practice it. I'm promising you there will be some sort of a question like that. Okay, we've got a few things to deal with here with some, I'm not sure if there are special rules or exceptions that relate to either regiochemistry or reactivity. And when you have two substituents that are meta to each other, like this case where there's two methyl groups, this is kind of simple because they're both ortho para directors. We have to decide where the third substituent is going to add. So the product of this reaction is going to still have the two methyl groups on there. And so in this case, it's arbitrary which one we say, since they're both equally directing. You can pick either one, since they're both equally directing. So if I look specifically here at this top methyl group, it's going to direct the next substitution to go ortho or para to that methyl group. And you'd get the same answer if we looked at this kind of if we looked at this bottom methyl group, the next substituent is going to go ortho or para. And so we're really trying to decide here, does this next substituent go here, both ortho to one methyl and para to the other, here or here? And our simple rule is that if you have a choice in these cases, don't add the substituent between the two alkyl groups or between the two substituents. It's just too hindered. This is a simple case of steric hindrance, which is not really in general that useful of a predictive tool. And so our next substituent, as long as I don't go between the two alkyl groups, either of these other positions with the question mark is going to give us the correct answer. So I'll put it here. This happens to have symmetry, so it won't make a difference. This is a Friedel-Crafts acylation reaction. And if we had a similar sort of a system where the two groups were not the same, we could use the same tool. So let me show you an example. Let me go ahead and just slightly change this to be a different substituent on a different set of substituents on here. So in this case, I'll put methyl group on top, and maybe I'll put a bromine here at the bottom. And you can do Friedel-Crafts with bromine atoms on there. They're deactivating, but they're not deactivating enough to stop a Friedel-Crafts reaction. from occurring. So if we did the same reaction with the same reagents, the propionyl chloride, this acyl chloride, and the aluminum trichloride, our prediction would be that you don't substitute here. I'll just put here, no. So we're going to go to one of these other positions. So our guess here would be that the most activating group here is the methyl group, and the methyl group is going to direct substitution either at the para position or at the ortho position, and you'll get a mixture of those. You would end up predicting, oh, I think I will get a mixture of those two products, right? And so the prediction would be you'd get a mixture, an awful mixture of two things, but that's the prediction. And so the predicted product mixture would involve, I'll put that methyl group down to make some room, para to the methyl, which is the strongest activator, and you'd also get the product of ortho to the methyl group. But we're not predicting that you would go in between the two, the methyl and the bromine. That's an ortho position where we wouldn't be predicting. So this would be the predictions. You get two products, but you wouldn't get the product of substituting between the methyl and the bromine. So that's a pretty simple rule to use. And sterics is usually kind of an obvious concept, you know, because it's easy to see when things look big or crowded. I think that's visually easy to handle things based on sterics. All right, we're going to shift gears here and now look at how do you take the substituents that you have on a benzene ring and do something useful with them. And I'm going to bring you back to a reaction from in the 5th edition of the Gorzynski-Smith textbook. We covered allylic bromination back in chapter 15.10. And if you were using the 6th edition, that would have been section 13.10. It was the chapter on radicals. And we taught you this reaction where if you have alkenes that have allylic hydrogens, here let me go ahead and draw one of the two allylic hydrogens, and you treat that with N-bromosuccinimide in the presence of light or heat or peroxides, you go through a radical intermediate when you abstract. I'll draw one of the two possible allylic resonance structures. Maybe I'll draw the other one. There's two possible allyl resonance structures you can draw for the intermediate. And when these trap out a bromine atom, unfortunately, you get bromination on both ends of this allyl radical. What an awful nightmare, because you end up with mixtures of bromine products, except in the case where your alkene has symmetrical substitution on both sides. And nobody wants mixtures of products. That's kind of a sucky situation. So I doubt you've seen this reaction since you covered it in chapter 13 or chapter 15, because it's pretty worthless because nobody wants to generate mixtures. And it's worse if we had a substituent on the other side, we would have even more allylic hydrogens to abstract. So that's not really a useful reaction there. But it turns out if we take those same conditions and we apply them to benzylic hydrogens, let's go ahead and draw those benzylic hydrogens in. Those benzylic hydrogens are here. There's two of them. I'm just going to draw one of them. This turns out to be a useful application of that same chemistry, the radical chemistry that we learned for allylic substitution. So in this case, it kind of looks allylic just like I've drawn up above here. The product of the reaction is only going to be one possible product. There's only one H here, and all you get is substitution of that allylic hydrogen. Right? That's all you get. You don't have to worry about which position of the allyl radical or benzyl radical gets substituted. You only get this. The only thing you have to be careful about is to look for the formation of stereogenic centers. So in this case, I formed a new stereogenic center, and you have no control over that. So you would end up getting this plus the enantiomer. I'm going to write plus E to represent the fact that there's an enantiomer in there. That's the mirror image of this one, where you would have a hashed bond instead of a wedge bond. And this is totally general. Now, unfortunately, the book tells you that there's other conditions you could use. You can even use Br2 and instead of N-bromosuccinimide. And you cannot do that with regular alkenes. If you use Br2 with a regular alkene, you're going to add bromine atoms across the double bond. But here with benzylic bromination, you can use any of these combinations of reagents. I don't know why the book tells you that. They ought to just give you one set of reagents. I'm just writing NBS and light, H nu, that's like the physics equation, energy equals H nu, symbol for for the energy of a photon. So that just means light. We've put energetic light into there. You can have other substituents on there. Doesn't stop it. We could have an isopropyl group. We could have a bromine already on the benzene ring. I have no idea how you would generate this meta-substituted. Maybe that's a puzzle for you to solve. If you could get your hands on this, I don't know how, right? The bromination won't affect the original bromine or chlorine or alkoxy substituents. It's only going to go after this benzylic hydrogen. I'll draw that benzylic hydrogen. It's going to substitute that. And why would you want to substitute a benzylic hydrogen with a leaving group? Well, that's kind of obvious. Now you can do substitution reactions. So now with that extra benzylic bromine, you can do SN, well, you can't do SN2 on this because it's too hindered. You could do SN1 reactions. You could do elimination reactions like E2, even E1. And in the next chapter, I'm going to show you another cool reaction you can do with alkyl bromides, which is to convert that into a powerful nucleophile. So keep this reaction in mind because it's not kind of boring to put alkyl groups on benzene rings. But when you can substitute those alkyl groups, then it turns into a useful reaction. Let's take a look at some more chemistry you can do with substituents that you put onto benzene rings. And we showed you how to put acyl groups on benzene rings using Friedel-Crafts acylation reactions. So you take an acyl chloride, you take aluminum trichloride, and you can add acyl groups onto benzene rings in order to make ketones. But we don't always want ketones on benzene rings. Sometimes we want alkyl groups. And there's just a whole set of problems that arise when you try to do Friedel-Crafts alkylations. I'll mention an issue with migrations shortly. But you can take these sorts of phenyl ketones and convert those ketone groups, the carbonyl groups, into CH2 groups through two sets of conditions. One set of conditions is boiling it in base, and the other set of conditions involves boiling it in acid. And the conditions are just absolutely brutal. They will trash any functional group that is either acid sensitive or base sensitive. So you really want to choose carefully your conditions. The fact is, let me go ahead and show you the product of this reaction. This initial one is called a Wolff-Kishner reduction. I don't care if you know what the name of that reaction. I'm never going to ask you whether that's a Wolff-Kishner reduction or below a Clemmensen reduction, but I want you to know these reagent combinations. So, oh, what have I done here? The point of this reaction is to remove that carbonyl. This replaces the carbonyl with a CH2 group. We usually don't draw the H's on there. And so this is the product of that reaction. Now, how would you decide which of these two conditions you're going to use when they look like they're mighty similar there, like they do the same thing? Here, you actually want to choose carefully the conditions that you're doing. So for example, let's suppose that I had some sort of a tertiary alcohol over here. Boy, I don't want to be treating that with hydrochloric acid and boiling it because it's going to lead to substitution of the alkyl hydroxy group with a chloride. There's lots of functional groups that you're going to see, or if you had an alkene hanging off of here, you don't want to add HCl across the double bond. There's all kinds of reactions you learn that HCl can do, and you don't want any of those reactions to occur. So what would you do in this case if you had an acid-sensitive functional group? Well, in this case, you use the base. The basic conditions, the hydrazine, this molecule here, H2N, NH2, is called hydrazine. In those cases, those conditions wouldn't have any problem with this tertiary hydroxyl group. It would survive into the very end. So if you have acid-sensitive functional groups, then use the hydrazine in base conditions. And if you have base-sensitive functional groups, like things that are sensitive to an E2 elimination, that's what bases do, then you would want to use the acidic conditions on the bottom. And if you have something that's both acid sensitive and base sensitive, well, you're kind of out of luck. At least you're not going to be able to convert the ketone directly into an alkyl group. Okay, be careful because a ketone is not an ester, and a ketone is not an amide, and a ketone is not a carboxylic acid. If you wanted to take an ester and directly convert that to a CH2 with the same alkoxy group on there, there's no way to do that. There is no reaction we are going to teach you because neither of these conditions above will work for this case. So we haven't really covered chapter 22 yet, which talks about the chemistry of esters and amides and carboxylic acid derivatives. But don't try to use these conditions above, because those conditions above are not for esters or amides. It turns out, though, there is a way to burn this carbonyl of an amide down to a CH2 group. And I'm not going to tell you what those conditions are. I'm just going to tell you it's a secret that you're going to see in chapter 20 that will tell you how to secretly do this without using hydrazine. Whoa, I'm running out of room here on the side of my screen. But there's a secret conditions from chapter 20 that we're going to teach you that don't involve zinc, mercury, amalgam. Oh, let me explain to this. This reagent over here is called zinc mercury amalgam. That's the way you say that. You take zinc powder and you treat it with a little bit of mercury, and the mercury coats the surface of the zinc powder particles. But that may look strange to you, but it's not a one-to-one ratio of zinc. It's mostly zinc with a little bit of mercury covering the surface of the particles and forming an amalgam with that. Okay, so powerful chemistry here, converting ketone groups that you might not want into alkyl groups that you do want. So this allows us to now talk about why you couldn't make those same compounds using a Friedel-Crafts acylation reaction. If you wanted to make that same type of product like this through a Friedel-Crafts acylation, you wouldn't get any of this product whatsoever, right? Let me just put a big X through that, because that's not what you would get in this reaction. What you would end up getting in this reaction would be a T-butyl group attached to your benzene ring. This would be the product of that reaction. You would have your original benzene ring. I don't know why I drew a different resonance structure there. That's not important. You would get T-butyl groups. So if you start with this isobutyl chloride, this primary alkyl chloride, you would not get a primary alkyl group attached to the benzene ring. And here's why. When you do this Friedel-Crafts activation, I'm not going to draw the whole mechanism here for you in this reaction, but if you do this, let me draw my lone pair a little bigger here. Remember, the first step of the reaction is that the aluminum trichloride, you form this Lewis acid complex, and then the aluminum tugs off that chlorine atom and makes a carbocation. But this carbocation that you generate here is going to be short-lived. Boy, that thing is going to be just screaming hot here. This primary alkyl chloride, right, that's primary, I'll just write primary R+, is subject to rearrangements. I can't remember which chapter you talked about this in, maybe chapter 9 or 8 of the textbook, when you talked about SN1 reactions and E1 reactions that generate carbocations. What you really want to have happen is you want the benzene ring to just cruise down over here and attack that. No chance, because the hydride migration is going to be much faster. You can't outpace that. That hydrido group, the hydrido substituent, is right there all the time, just sitting there waiting. Long before any benzene rings collides with this, it's going to go boop and migrate right over. And you cannot stop that. You can't win against that process. It's too fast. Let me just write fast. Oh my gosh, that is fast, because primary alkyl halides are so crazily unstable and so reactive. And so that carbocation center, we called that type of carbocation a carbenium ion, would be so much more stable. This would be a very fast rearrangement. And now this T-butyl carbocation will just sit there until it finally collides with a benzene ring. And I'm not going to show you the mechanism for Friedel-Crafts addition of a carbocation. We've already been through that before. So you're not going to be able to, if you wanted to generate this product up on top, remember, if you wanted to generate this, you've got to acylate and then use one of those reduction conditions, the Wolff-Kishner or the Clemmensen reduction that I just showed you on the last slide. That's the way to make this product with the X through it. So let me go ahead and show you how you would use that two-step process to affect that transformation. If you wanted to take a benzene ring and add this isobutyl group with a CH2 group here, you can't do that in one step. What we have to do is we have to do step 1, and you have to enumerate these steps. Don't just write out every reagent for all the steps here. Step 1 would be to do the Friedel-Crafts acylation, like this. which would put a carbonyl group where the CH2 is. And we have to remember the aluminum trichloride there to put that in. And then step 2 would be, and I think the book, you know, when I enumerate reagents, you've got to be careful to follow along with the enumeration of the reagents. I think the book uses brackets around its enumerated reagents. I usually use a period, or I use a single, you know, what are the ways? The book usually does this. It puts these kinds of brackets around the enumerated steps to make sure you understand that you're isolating the products in between and purifying them before you go to the next step. And I usually use periods, or I draw a little half parentheses there. But the important thing is to enumerate the steps. And if I use Arabic numerals, it means I'm trying to convey to you that we're purifying the products after step 1 and then dumping them into step 2. Step 2, I showed you a set of conditions. We could use either those zinc, mercury, amalgam, and acid conditions, or the hydrazine and base. And for some reason, I just arbitrate. There's usually more acid-sensitive functional groups than base-sensitive. So I usually, as a first choice, write out the base reaction, the hydrazine, and sodium hydroxide, and heat as my first choice, because base-sensitive substituents are less common than acid. So I usually like the basic conditions. They're harsh conditions, and that's a delta symbol here for the below that, which is intended to mean boiling at 100 degrees, an aqueous solution of hydrazine. All right, you know, we want to convert substituents that we know how to put on there to things that we really want. And I mentioned before that medicinal chemists don't really want nitro groups on their benzene rings. They just cause problems with toxicity and metabolism. I don't understand the origin of that. I suppose I could look that up. Maybe that's something we should talk about at some point. So most medicinal chemists, and I usually think like a medicinal chemist, want to convert nitro groups to amines. And there is a super easy way to do that, that you already know the reagent conditions. It turns out that hydrogenation conditions will convert, if you just use hydrogen and then catalytic palladium on carbon. I usually write the word cat to indicate that the palladium on carbon is catalytic. That's a capital C, by the way. But the book doesn't indicate that. They just expect you to know that the palladium on carbon, you just add a pinch of this black powder, palladium on carbon, into your reaction, and fill a balloon with hydrogen and with a little needle stuck in the end of the balloon and stir it around. It's that easy. And you get the aniline byproduct, or the aniline product out of the reaction, and it's usually quantitative. And the only byproduct that you get, I'll just write it over here because we don't care about it, is water, which you can easily remove when you put it under vacuum. What a beautiful reaction. Yields always 100% for that. Now there's a slight problem where you might not want to use these conditions. So for example, let me just, I'll sketch out on here. What would happen if you had an alkene on there? Well, you're going to burn that alkene down to an alkyl group, and you don't always want to do that. So what would you do? We've got a second set of conditions that involves 2 steps that won't touch alkenes, and it won't harm alkyl aryl bromides or aryl chlorides. It turns out that aryl chlorides and aryl bromides get cleaved by hydrogenation conditions. So if you wanted to keep that aryl bromide on there, you can't hydrogenate. It would convert that back to an H. And if you just spent a lot of work turning an H into a bromine, the last thing you want to do is to remove the bromine and put an H back there. So whatever our conditions, it's a 2-step process that we need for this. And the conditions involve step 1, tin and hydrochloric acid. And it's just powdered metal tin. We have other tin reagents that we use, but this is the simplest set of conditions. And noticing that I'm using this little Roman numeral I, when I use that, I'm usually trying to indicate to you that we just pour one set of reagents in, and then without purifying anything, we pour the next set of reagents in. But if you used Arabic numerals, that's okay. That's the way the book does it. But if you're wondering, gee, why does Van Vranken sometimes use those little Arabic numerals? I'm trying to distinguish by using the Roman numerals here that we don't purify in between the 2 steps. The next step here is really part of our workup, because under the acidic conditions, the product of the reaction is the protonated amine. And nobody wants that. We don't like salts usually. We like to isolate neutral organic products that we can extract into organic solvents and easily evaporate. So it's a two-step process. Step 1, tin, hydrochloric acid. Step 2, we use a sodium hydroxide workup to free up the amine. And we're going to talk a lot about these acid-base, using basic workups on amines or ammonium salts when we get to chapter 25. That's chapter 25 is all about amines and what's called freebasing protonated amines. So again, you couldn't, if you tried to use the hydrogen and palladium on carbon, you would have cleaved the carbon-bromine bond here. Okay, so so again, two sets of conditions. By far, the hydrogen and palladium on carbon is the most common, because it's not that often that you happen to have a chlorine or a bromine or an iodine substituent on your benzene ring, or some sort of alkene float in there attached to it that you don't want to hydrogenate down. That's not that common. Now, we've shown you a lot of reactions in this chapter, chapter 18, and we want you to think strategically about how to use those reactions. And so this is the kind of problem that you can solve now with the reactions that we've shown you in chapter 18, such as something that looks very simple. How do you take a benzene ring and add a nitro group and a propyl group? And there's a couple of problems here. One is the regiochemistry, because I asked you, how do you put those on there so that they're oriented para to each other? Okay, that's a little harder than you might think. And moreover, how do we attach a primary alkyl group to a benzene ring without undergoing hydride rearrangements? So that's really the trick here. Generally, when I ask you about multi-step syntheses, there's two directions you can go. One is you can try to figure out every possible reaction you know that makes either a carbon-nitrogen or a carbon-carbon bond starting from the starting material. I mean, you've got to make a carbon-nitrogen bond or a carbon-carbon bond. So you could start off by saying, okay, let me list every possible reaction I know to make carbon-nitrogen and carbon-carbon bonds. The other way you could do these types of problems is to work retrosynthetically, to work backwards from the final target. And you could say, what's every reaction I know that could have put on the nitro group, or every reaction I know that could have built this propyl functional group on there. So, and you won't always know what's the right way. Maybe it depends on, did I memorize more reactions of benzene rings, or did I memorize mostly reactions of nitro and alkyl groups? So, you know, the way I might approach this is I might start to work backwards. I might try to say, well, gee, you know, if I could just put on, if I knew how to put on a nitro group here, I'm going to erase in a second. Do I know any way to put a functional group para? And the answer is no. There's no way. If you start with a nitro group, it doesn't matter whether you do Friedel-Crafts acylation or alkylation, you're not going to be able to put any functional groups para, because nitro groups prevent you from doing Friedel-Crafts chemistry. There's too deactivated. So you're really, the last thing you're going to have to do here is you're going to have to put on, you're going to have to start with the alkyl group maybe, and then do a nitration reaction. So there's no way to selectively nitrate para. The only thing you can really do is do a nitration and generate a mixture of ortho and para. I'm still kind of working backwards here, right? If we had a way to put a propyl group on a benzene ring, we could do that. And anytime you generate mixtures of ortho and para, I will allow you to use the word separate to pretend you're doing a separate chemical step to isolate either the ortho or the para product. So really all you need to do, anytime you generate mixtures of ortho and para, I'll allow you to pretend that separation of one of those two is a step that you can do. And we have ways to do that, typically silica gel chromatography. So if you could put a propyl group on there, then there is a way to substitute ortho and para, and that would just be using simple nitration conditions. I hope you've memorized these conditions by now. It's nitric acid, and then as a catalyst you use sulfuric acid. There we go. That's it. But how do we put the propyl group on there? There's not a one-step method that you could use for this. You can't just put propyl chloride in and do a Friedel-Crafts because that would undergo hydride migrations. We have to do this in 2 steps here. The way we put these types of functional groups on there is we first acylate a benzene ring with a propionyl group. And then I just told you conditions where you can burn down that carbonyl to a CH2. Since there's no base-sensitive functional groups on here, I'm going to use those hydrazine and base conditions. Hydrazine, sodium hydroxide, and you boil it, you heat it. You can use the delta symbol for that. We could also use the zinc mercury amalgam and hydrochloric acid and heat. That would work fine. And how do you put an acyl group on a benzene ring? Well, we know how to do that. That's Friedel-Crafts acylation. So we take the acid chloride, the acyl chloride, and we add our catalyst in there. It's aluminum trichloride. And there we go. So this would be a viable route to do this. Notice that you couldn't directly nitrate the acyl benzene first. If you tried to acylate this, let me use a red pen to indicate this is going to go. If you tried to nitrate this, it's not going to go para. You would end up getting as a product something you don't want that could never be converted into the final product. This would lead to a dead end for you. You'd be stuck here with a nitro group at the meta position, and there's no way to work that out. So this looks like a very simple problem, but it's actually a very tricky strategic problem that requires you to know a bunch of transformations and a bunch of exceptions related to electrophilic aromatic substitution. So I've made this important point down here at the bottom that whenever I ask you to efficiently synthesize a molecule, you can just assume that separation of ortho from the para isomer, or the other way around, separation of the para from the ortho isomer, is an efficient chemical step, even though you really are generating those in about 50-50 mixtures. So just remember that. Okay, that's all the material. I'm pretty sure that's all the material here for chapter 18. So I want to encourage you to work sapling problems. Work those sapling problems. I realize you can probably find the answers posted somewhere on Chegg. You know, the answers are slightly, I think the problems are slightly modified from some of them might have been in the spring quarter. Don't do that. Please work the problems. Work every problem you can get your hands on. When we get to the exam, I'm going to give you problems you've never seen before. So the more practice that you've had working problems you've never seen before, the more likely you're going to be able to work those problems on my exams. So great job. Try to interact with other students, get to know other students in discussion section, form study groups, test each other, talk about chemistry. And thanks for joining me here on our lecture here, our fourth lecture here in Chemistry 51C. And I will see you guys on Monday.